Welcome to this explainer. You know, when we think of hacking, we usually picture some shadowy figure in a hoodie typing furiously in a dark room. But today, we're going to completely flip that script. We're diving into the true art of programming and computer memory. And to do this, we're going to follow a classic mentor-student journey. Meet Arjun, a super curious beginner coder, and his mentor, the wise cyber guru. Together, they're going to show us that hacking isn't what the movies make it out to be at all. It's actually a highly creative art form.
So where do you start when you want to learn hacking? Well, the guru doesn't just sit Arjun down in front of a terminal and say, "Start coding." Nope. He actually hands him a math puzzle. He says, use the numbers 1, 3, 4, and 6 exactly once with any of the basic math operations to total exactly 24. Right? What does that have to do with computers? Well, everything. It's all about finding completely counterintuitive solutions within a very rigid set of rules. I mean, think about how you'd solve it for a second. Okay, I'll just give you the answer. The trick is 6 divided by the result of 1 minus 3 divided by 4. You literally have to think entirely outside the box to get there. To really wipe Arjun's slate clean, the guru contrasts two totally different mindsets for us. See, the media loves to paint hackers as just electronic vandals, thieves, or basically unskilled script kiddies, just out to make a quick buck. But the true hacker ethic? That actually dates way back to the MIT Model Railroad Club in the 1950s, and it is something completely different. These folks were artists. They were innovators. They were driven by a deep, deep appreciation for logic, elegance, and finding the absolute beauty in a perfectly solved problem. Code as everyday directions. Let's look at how this philosophy applies to actual computers. The guru explains it simply. Programming is just writing a recipe.
At its absolute core, coding is incredibly intuitive. You're really just giving the computer a very clear set of everyday directions, guiding it step by step through a task. Think about it like giving someone driving directions. Step 1, drive down Main Street. Step 2, if the street is blocked, turn right on 15th Street. Step 3, turn left on Pine Street. And Step 4, turn right on 16th Street. Literally anyone can understand that logic, right? Well, programming a computer is exactly the same thing.
Now, when we translate those driving directions into what we call pseudocode, we start to see how control structures let a computer make decisions on the fly. Without statements like if, then, else, or while loops, a program is kind of dumb. It just runs blindly in a straight line. But the second you introduce these structures, suddenly, if the street is blocked, then it knows to take a detour. It takes those simple sequential steps and magically turns them into complex adaptive logic. It's a real game changer.
Speaking the machine's language, so how does a computer actually read these English-like words? Because at the end of the day, hardware really only speaks in ones and zeros.
To explain this, the guru maps out the layers of translation. Up at the top level, we've got high-level intuitive languages like C or Fortran. This is the English-like stuff. Then a translator called a compiler takes that elegant code and translates it down into a mid-level language called assembly. Finally, an assembler steps in and grinds that down into raw machine language at the very bottom. That's the arcane hexadecimal and binary that the processor actually natively executes. It's like translating a novel into a completely different alphabet, step by step.
Mapping the computer's memory. To truly master the art of code, it's not enough to just write the recipe. We absolutely have to look at the kitchen where the cooking actually happens.
When we peel back those layers of abstraction, we find 5 distinct segments of computer memory. We have the text segment, which holds the assembled machine instructions. Then there's data and BSS, which hold different types of global variables. But the real dynamic action, that happens in the heap and the stack. This is basically the hacker's playground. The heap is dynamic memory controlled by the programmer, and it grows downward. The stack is a temporary scratchpad for function calls, and it grows upward. And here's a cool detail. Because they grow toward each other, they actually efficiently share the available memory space.
Now, Arjun was struggling a bit with this concept of the stack, so the guru gives him this amazing analogy. Think of the stack like beads on a piece of string with a knot tied at the bottom. It's a first-in, last-out data structure, or FILO. If you slide 3 beads onto that string, you literally cannot get that first bead back off until you remove the top 2. It's the exact same with the computer. When a program jumps to a new function, it pushes variables onto the stack, and when it finishes that function, it just pops them right back off.
As you can see here, this is the actual architecture of a stack frame, and this perfectly visualizes how a program remembers exactly where it needs to return after calling a new function. It holds those local variables we just talked about, but crucially, it also holds 2 more things: a saved frame pointer and a return address. It's kind of like leaving a highly specific bookmark in a textbook while you go check the glossary. Once you're done looking up your word, that return address tells the processor exactly where to pick up reading again.
The art of exploitation. Okay, so with this blueprint of memory all laid out, Arjun is finally ready to see how that hacker ethic turns into actual, real-world exploitation.
And the guru explains this by telling a joke about a very literal-minded genie. So, a guy tells the genie, "I want to be irresistible to women." The genie snaps his fingers, and the man turns into a literal box of chocolates. Well, that's exactly how programs written in languages like C behave. They have absolutely zero common sense. They execute the laws of their programming to the absolute letter, even if that results in something entirely unexpected by the programmer who wrote those laws.
And folks, this right here is where the true art of exploitation happens. See, a programmer intends for the stack to just hold temporary variables, right? Just standard execution flow. But a clever hacker realizes that if they provide an input that's much longer than the programmer prepared for, that input spills over. It overflows its designated space. It crashes down the stack and overwrites that critical return address bookmark we talked about. So now, when the function finishes, instead of returning to the normal program, the computer literally follows that new overwritten address straight into the hacker's custom malicious code. Boom, the system is hijacked.
It's fascinating, right? This constant back-and-forth competition between attacking and defending hackers is exactly what drives the evolution of better security. Finding these loopholes forces developers to write safer, tighter software. It is a continuous co-evolution. Without hackers, our tech world would just stagnate. There'd be no curiosity, no true innovation. So, we're going to leave you with this final thought. In a world defined by complex systems and rules, will you choose to just blindly follow them, or will you look close enough to master them?